Now we are going to talk about multipliers. A multiplier is a combinational logic circuit, and this is used to multiply binary digits. And this multiplier also known as a binary multiplier or a digital multiplier. And this multiplier is same as adder and subtractor. It is also a arithmetic logical circuit. So these multipliers are used in several digital signal processing applications like calculators, mobiles, processors and digital image processors like that. And there are some varieties of this multiplier. For an example, we can take 2-bit multiplier. And another example is 3-bit multiplier. 2-bit multiplier. As the name suggests, this 2-bit multiplier multiplies 2 digits. Each digit contains 2 bits. So we can construct this multiplier using 2 half adders and several AND gates. And in this circuit there are 4 inputs and there are 4 outputs. We can I'm going to explain about these inputs and outputs in our explanation. So let's move to that. Now we are going to describe the function of a 2-bit multiplier. So let's first draw this multiplier. As this multiplier multiplies 2 numbers that has 2 bits, so this multiplier has 4 inputs, which are A1, A0 and B1, B0. So this is a multiplier of 2 numbers. Each number has 2 bits, so the output will be a 4-bit number. So there are 4 outputs, which are P3, P2, P1 and P0. So let's get the first number, the first 2-bit number as A1, A0, and the second number as B1, B0. So let's multiply these 2 numbers. So as we do the binary multiplication, A1, A0, B1, B0, we multiply this. So in the first row, we are going to write the multiplication of A1, A0 by B0. So first we have, by multiplying B0 with A0, A0, B0, and we multiply B0 with A1. It is A1, B0. So let's move to the other bit. So we multiply B1 by A0. So in here we write that multiplication in here. Let's do it in another color. It is A0, B1, and we multiply B1 by A1. A1, B1. So now we have to get the summation of these 2 lines. So let's get it. In here we get A0, B0. In here we are getting, as there are 2 values, we get the summation of these 2 values. So A1, B0, or A0, B1. So as this is a summation, there can be a carry out. So there can be a carry out. So this carry out is going to this. So for the summation of this, column, we have to get the summation as A1, B1, O, C. Let's name it as C1. So this is the summation for this row, and as we mentioned earlier, the 2-bit multiplier has an output with 4 bits. Let's get the 4th bit. So as this is also a summation, there can be a carry out. So we name it as C2, and this C2 is going to be there, and this C2 is coming as the 4th bit. So here is the C2. So we can get the outputs. So A0 B0 is P0, and A1 B0 or A0 B1 is P1, and A1 B1 or C1 is P2, and C2 is P3. So now we can get the expression for both P0, P1, P2 and P3. Let's write them down. P0 equals to A0, B0, and P1 equals to A1 and B0 or A0 and B1, and P2 equals to A1 and B1 and A1 and B1 or C1. So P3 equals to C2. So these are the equation for our 2-bit multiplier. Let's implement this multiplier in our logic simulator. Now we are going to demonstrate our 2-bit multiplier in our logic simulator. So these are the equations that we find out before. Let's start. As there are 4 inputs in this multiplier, I am going to define them. I am going to define the input like this because I want my circuit to be more clear. So this input is A0. Okay, I use here a connector. So let's get other 3 inputs like this. So here are our all inputs, and we can say there are 4 AND operation in here, in here, in here and in here. So we have to get 4 AND gates. So let's get the first AND gate, and for this AND gate the inputs are the first AND gate A0 and B0. So let's connect it. I use here a connector. So this is A0, and for the second input of this AND gate it is B0. So let's get other 3 AND gates like this. So here are all the AND gates. So this AND gate is for this, and this AND gate is for this operation, and this for this operation. So we can say the result of this AND gate, the AND operation of A0 and B0 is equal to P0. So let's get that output. So this is P0. I'm going to name it. This is P0. And we can say there are for the P1 there is an addition. So we for this we use a half adder. So for a half adder, the summation will be the XOR operation of these two inputs, and the carry out will be the AND operation of these two inputs. So here are these two inputs, this AND gate and this AND gate. So at the first step of the half adder, I'm going to get the XOR gate. So I place it here, and for this XOR gate, the inputs will be this AND gate and this AND gate. So I'm going to connect it. So the summation, which means this P1 will be the output of this XOR gate. So I'm going to name it. It is P1. So there is a carry out, as this is a half adder. We have to define it. So I'm going to get an AND gate to here. Okay, the inputs for this AND gate will be this and this. So I'm going to connect those. And this. So this output of this AND gate is C1, which is the carry out of this first half adder. So we can see for the P2 there is also a half adder. The input for this half adder is AND operation of A1 and B1, this AND gate, and C1, this output of this AND gate. So let's build it. As the first step for this half adder, like previous, I'm going to get an XOR gate, and I'm going to connect the inputs for this XOR gate. And this P2 is equals to summation of these two. So the output of this XOR gate will be P2. So I'm going to name it as P2. So as this is also a half adder, there is a carry out. So I'm going to implement that. So for that I need an AND gate. To that the inputs will be this AND operation of this and this, A1 and B1 and C1. Okay, C1 is the output of the carry out of this half adder. So I'm going to connect this, and the other input is this. Okay, so the carry out of this second half adder will be equal to P3. So I'm going to name it. And I'm going to move these outputs little bit that side. Okay, so now this is the circuit for our 2-bit multiplier. Let's check this circuit with an example. As the example for our multiplier, we get the multiplication of 3 and 2, and it equals to 6. So let's get the binary form of this 3 and 2 first. We can get the binary form of 3 as 1, 1 and So our A0 input will be 1 and A1 input will be 1. So let's get the values for 2. So we can write 2 in binary form like this, 1, 0. So we can get our input values for B0 is 0, B1 is 1. So let's get the multiplication of these two binary numbers. It is like this. So we multiply 0 by 1, it is 0, and 0 by 1 again, it is also 0. So then 1 by 1, it is 1, and 1 by 1 again, it is 1. So then let's get the summation of these two number lines. In this line, this is as there is no value for this, so it is considered as 0. So 0 plus 1 equals to 0. Then here 0 plus 1 equals to 1. So here it is considered as 0. So 0 plus 1, it is 0. So it is 1. And then as we mentioned earlier, the multiplication of 2-bit numbers, the output has maximum. Output can have maximum 4 values. So this is the fourth value. So we consider it as 0. So these are the output values. P0 is 0, P1 is 1, P2 is 1, and P3 is 0. So let's move to our simulator and let's check this example. So now we are in our simulator. This is the input values for our example, and these are the output values for our example. As input values, the A0 is 1 and A1 is 1 and B0 is 0 and B1 is 1. So here is the output. We can see P0 is 0 as expected, and P1 is 1 and P2 is 1 and P3 is 0. So this logic circuit, this circuit for this 2-bit multiplier is correct for our example. So this is how the 2-bit multiplier works.